Is it fine now to all? Yeah. In the previous class, we discussed about the normal extensions. So, anybody has any queries on this concept so far discussed? Any queries you can ask? Yes or no? Is it clear for all? Everyone? Right? So, can we continue the class now? Thank you. So, this is the problem I have taken. So, this is the problem I have taken. If E is an extension of F such that dimension of E over F is equal to 2, then we have to show that E is normal extension of F. So this is the problem I have taken right now. Now, in today's session, I will take the concepts based on normal extension as well as algebraic extension and other things. Then we will discuss with the separable extensions and some basic definitions, right? There we can conclude our today's session, and in tomorrow's session I want to give the problems based on silo theorems with respect to group theory. So for the upcoming session, I request you to take the concept of group theory fundamentals once. Then we do the problems based on silo theorems. If possible, I will give the statements of silo theorems in today's session itself. Then we go for the tomorrow's session, problems based on the theorems. Okay? That was the upcoming module with regard to abstract algebra. Is it clear to all? So coming to the problem, this is the thing he asked actually. In particular, if the dimension is a prime number, in such cases also, we can say that E is normal extension of F. So, first of all, as it is given that dimension of E over F is equal to 2, it means that basis contains finite number of elements. So, can we say that E is finite extension of F? Say, am I correct? Then, as we know that every finite extension is algebraic, we say that E is algebraic extension of F. E is algebraic extension of F. Now, if you take the hierarchy, this is F and this is E. Now let us take an element in E which does not belongs to F. So we can say that we can have a subfield between these two, f of alpha and e, and the hierarchy will be like this. This is a proper subset of f of alpha and this is a subset of e. All of you accept it? Yes or no? Say. Now, if you consider the dimension for this one, E over F is equal to E over F of alpha into F of alpha over F. As per the problem, this value is 2. So 2 is equal to product of these two values. Since 2 is a prime number, the only possibility is among these two things, one value should be 1, the other one will be 2. So we can say one thing that as f is proper subset of f of alpha, as the hierarchy you have taken, because alpha belongs to E, taken such that alpha does not belongs to f. So this is a proper subset of this is a subset of this. Hence we can say that this will be 1 and this will be 2. Because if you take f of alpha over f is equal to 1, then we have done similar problems on this. Immediately we can say that f is equal to f of alpha. But this is a contradiction. These two are different sets. So the only possibility for this position is 2 only, and this will be 1. Since this value is 1, immediately these two will become equal. Any questions for anybody so far? F of alpha, I have taken just as an extension. I didn't mention that f of alpha is a proper subfield of E. I didn't mention, right? I will give a small example. Suppose we have taken Q. If you take Q of root 2, you can take the other hierarchy also. Then what happens? Root 2 does not belong to Q accepted. So we can say that Q is a proper subset of Q of root 2, say. Isn't it? Now you got the answer. Do you accept for it or not? The thing what I have written there. So these two will be equal and this value is nothing but 2. Any other questions please for anybody? If you are clear, I proceed further. Fine. Now what happens? As we know that f of alpha over f is equal to 2. It means that this alpha is algebraic over f. Hence, it satisfies a polynomial over f. And what will be the degree of the polynomial? It is nothing but 2. So let us take that the minimal polynomial satisfied by alpha is nothing but 2, has degree 2. And that polynomial is p of x. Let us take that. This is the minimal polynomial having degree 2 satisfied by alpha over f. Now what happens? Since alpha is one root of it, immediately the other root also belong to the same set. Are you getting it or not? Audio, right? Fine. Therefore, at this point of view, if alpha is one root of the polynomial, the other root is also belonging to the same set f of alpha itself for the polynomial p of x. Since E is equal to f of alpha, this is the splitting field, hence it will become the normal extension. That was the conclusion. Because normal extension is nothing but whenever you take a polynomial, the splitting field is nothing but E. If you have shown that, then E will become the normal extension. That's all. Okay? Right. Now, I want to discuss some small things. In the previous class, we have learned about algebraically closed fields, right? I have given the definition also. Can you recollect the definition once from your side? There is one good result based on this. There are four conditions based on algebraically closed fields, and all the four conditions are equivalent. It means that if one condition is satisfied by the set, the remaining three will be also satisfied by the set. So these four conditions are equivalent. The condition is, suppose K is a field, let us take that. The first condition is K is algebraically closed. The second condition is every irreducible polynomial belonging to K of x has degree 1. And next one, every polynomial belonging to K of x of positive degree splits into linear factors in K. Completely. And the next one is every polynomial of positive degree belonging to K of x has at least one root in K. these are the four conditions which are equivalent. You can say 1 implies 2, 2 implies 3, 3 implies 4, 4 implies 1, like that. So whenever we have one statement given, the remaining three statements by default apply. So while proving certain results, these are useful for us. Okay. The proof is not that much important. However, we discuss a small problem based on this. Again, if you talk about algebraically closed, so the field what you have taken should not possess any extension. That we need to confirm. Should not possess any algebraic extension. Let me say, if you take the example what I have given earlier, so suppose if you take that this is normal extension of this, let us assume that this is normal extension of this. So for this one, further extension is possible, isn't it? So it cannot be algebraically closed. Say yes or no. So splitting field or normal extension, we cannot say that it is algebraically closed. In other words, we can say one thing, that from the very word algebraically closed, since the four conditions are equivalent, from this every polynomial of positive degree splits into linear factors itself. So whatever the polynomial you take in the field, the factors are in it only. There is no need to search for the roots for the next set. All the factors will be within the field, right? So what happens? It is algebraically closed. So it is the splitting field and it itself is the normal extension. Okay? Because extending further is not possible. Are you clear now? Right. So the thing what I need to mention is, if you take any field, for every field we can find an extension which is algebraically closed, right? That is one good result. So every field will possess the algebraic closure. That I want to say actually. So if you take any field, we can get an extension for it which is algebraically closed. In other words, every field will possess the algebraic closure. Okay? Did you get the context? Now see, you take a field F and you consider an extension K for F, and I am saying that this is algebraically closed. That means for this field you cannot extend it. Now I want to say that the field possesses algebraic closure. So what does it mean? An extension which is algebraic and it is closed is called algebraic closure. So to prove this criteria, I will define a set between these two. Say I am giving the name F bar, and it is defined as F bar is equal to set of all elements in the set K such that it is algebraic over F. In other words, I have taken f bar as algebraic extension of f. So my intention is, if I prove that these two are equal, then what happens? This is the algebraic extension as well as it is closed. Hence, f possesses the algebraic closure. Okay. Again, I repeat, what is meant by algebraic closure? If I say I have a field f, I can find an algebraic extension which cannot be extended further. Such extension, I am calling it as algebraic closure. Okay? Are you getting the idea or not? So, as per the perspective, this is algebraic extension of f. This is the closed field. Further extension is not possible. If I say that these two are equal, then what happens? F bar is nothing but algebraic extension as well as algebraically closed. Hence, we say that the field possesses algebraic closure. That is the concept. Okay? All of you. Yes or no? Right. Now, let us take a polynomial. F of x belongs to f bar of x such that f of x degree is greater than or equal to 1. Now what happens? Whatever the polynomial you take at this position, by default this polynomial will belong to this because this is subset of this. Now what happens? Since this is algebraically closed, I have mentioned 4 conditions earlier. Using one of the conditions, I can say that there exists at least one root in K for the polynomial. Therefore, there exists a root A belongs to K for f of x. That is f of A equal to 0. Any questions for this step to anybody? Now, in other words, if you have a small hierarchy, the picture will come like this. So I have taken A here. I am saying that A is algebraic over f bar because A is satisfying a polynomial there. Therefore, we can say that f bar of A is algebraic extension of f bar. So you have the other thing. You have one more hierarchy, f bar of A. So you need to understand like this. F subset of f bar subset of f bar of A. So, as we know that this is algebraic over this, automatically the same element will be algebraic over f also. Do you accept it or not? We have solved a problem also. Whenever you take a hierarchy, if one element is algebraic over the previous one, the same element will be algebraic over the first one also. So, A is algebraic over f bar as well as f. Now see how the set f bar is defined. I am selecting the elements in K which are algebraic over f. So the value A is algebraic over f. Therefore, I say that A belongs to f bar. Therefore, K is a subset of f bar. Now what happens? As per the first hierarchy, what I have considered, f bar subset of K. So at this position, I have proved that K subset of f bar because A is an element in K and which is belonging to f bar. Therefore, K and f bar both are equal. That means these two sets will become equal. So f bar is nothing but algebraic extension of f as well as it is algebraically closed. Therefore, f bar is the algebraic closure of f. That was the conclusion. You just try to understand that. Then I will take the other concept. After noting, you please inform. Now, the question what I am going to discuss now is given in the previous papers. It is also a very simple one. Let us take that. So I have taken a hierarchy like this. F, K, L. So what I am saying that K is algebraic extension of F, and also I am saying that L is algebraic extension of K. So my task is L algebraic extension of F? Did you get the concept? If you take the hierarchy like this is algebraic extension of F, this is algebraic extension of K. Now the question is, the topmost set is algebraic extension of the smallest one or not? Clear? Please take a note of the question. This question is given in the previous year papers. Now see, what is meant by algebraic extension? Whatever the element you take in L, it must be algebraic over F. It means that the value what you are considering in L must satisfy a polynomial whose coefficients are taken over F. That was the idea. So first of all, let us take that A belongs to L. Immediately, I can say that since this is algebraic extension of K, there exists a polynomial f of x over K such that f of A is equal to 0. A is the root of that polynomial. So we can define the polynomial like f of x is equal to alpha naught plus alpha 1 into x plus alpha 2 into x square plus so on plus alpha n x power n. And A is satisfying this polynomial. Did you get that? Yes or no? Now, if you understand, while writing this polynomial, the coefficients, whatever the coefficient you consider, except this constant, alpha 1, alpha 2, so on, alpha n, all these coefficients are belonging to K. Since K is algebraic extension of F, so you have alpha 1 algebraic over F, alpha 2 algebraic over F, so on, alpha n algebraic over F. So if you collect all these elements together as a set, you give a name, because all these elements are algebraic over F. This set is the algebraic extension of F because it is containing all the algebraic elements over F. So for convenience, let us give a name for it. Let M is equal to F of alpha 1, alpha 2, so on, alpha n. And since it is containing a finite number of elements, this is a finite extension as well as this is the algebraic extension over F. You just take a note of that part. So this is also a constant, right? So while considering the constant, it is just a number by default. It has a chance of belonging to F also. The constant by default will belong to, if you have a doubt, you can include alpha naught also. No doubt at all, right? Each and every element. You take that. The polynomial may be of any kind. So you include alpha naught also. Say M is equal to F of alpha naught, alpha 1, so on, alpha n, right? That clarifies your doubt. So that is a finite extension as well as algebraic extension. Right. Now I will write something. Just take a note of this. Now you consider the thing that, see, A is a value satisfying this polynomial. All the coefficients in this polynomial are taken as a separate field like this. Alpha naught, alpha 1, so on, alpha n. Since the element A is satisfying a polynomial over this field, because this field exclusively consisting the values of this polynomial. So A is algebraic over M. So M of A is the corresponding extension of M. So if you draw the hierarchy, it will come like this. F. For this we have F of alpha naught, alpha 1, so on, alpha n. Then this number is taken as m. Here I have taken m of a. Now I have considered the hierarchy like this. So then you will get k, then you will get l. This is the hierarchy. So I have calculated the dimension of these two, m of a over m and m over f. So this is a finite extension. Why? Because the degree of the polynomial here is n, so this is finite extension. And this is also finite because this set contains finite number of elements. So finite value into finite value, the resultant is finite. Therefore, m of a over f is a finite extension. Every finite extension is nothing but algebraic. So a is algebraic over f. Actually, a is belonging to L. Therefore, L is algebraic extension of f. This completes the proof. However, the logic seems to be somewhat confusing, but you just remember the hierarchy while presenting on paper. That is enough for you. You take a note of that. So actually, always we get a doubt that since we are talking that if you take a field, then we can find an algebraically closed for it, closed field for this. Now the question is, if you take a finite field, is it algebraically closed? Now the question is, if you take a finite field, is it algebraically closed? That was the question. It is also a small question given in the previous year papers. The solution is very simple. So can I erase this part? Tell me. A finite field is not algebraically closed. You just take a note of that. Then we discuss about the solution. After noting, please inform. The solution is simple. Suppose you take a finite field K. Since it is finite, it means that it contains finite number of elements. Now see, as we have taken a set of conditions for algebraically closed field, among that, so if you say that a field is algebraically closed, then from the four conditions, whatever the polynomial you take over that field, at least one root should belong to the set. Am I correct? I have given the four conditions earlier. Please cross check them. You can take any kind of polynomial over the field. Definitely, it must possess one root in the field itself. Other roots may belong to the other set, that we don't bother, but at least one root definitely should be there in the set. Now, that is the condition for algebraically closed. If it is not algebraically closed, so what does it mean? If I am able to define a polynomial such that no element in this set will become a root of the polynomial, because one root is enough. All these n elements are not at all the roots of that polynomial, then I can say that this set is not algebraically closed. Now, the thing with me is how to define the polynomial. Now, I am defining the polynomial as, since it is having n elements, I will take the polynomial like this. Now see, this is a polynomial. If you substitute any element a1, a2, so on, an in this polynomial, they will not satisfy this equation. So these are not at all roots of this polynomial. Therefore, this is not algebraically closed. That was the conclusion. Clear? It is possible because this is the finite set. If you take infinite set, then you cannot define a polynomial in such a manner, because it is consisting of infinite number of elements, right? That was the issue there. You please take a note of that. Now, earlier we have discussed one part that every finite extension is algebraic and every algebraic extension need not be finite. So for that, if you want an example, how can we say that every algebraic extension need not be finite? We can have a small example like this. The example is, you consider the field E defined as Q of root 2, root 3, root 5, so on, root P, and so on. This is the field I have taken. So please understand how it is defined. We can have set of prime numbers, the positive prime numbers, 2, 3, 5, 7, 11, so on. So for all these prime numbers, you will consider square root. They are the irrationals. So all these irrationals are added to the field Q. This is the new field I have obtained. Now I say that this field is the algebraic extension for Q. This field is the algebraic extension for Q, because every element you consider will satisfy a polynomial over Q. If you take root 2, the polynomial satisfied is x square minus 2. If you take root 3, x square minus 3. If you take root p, x square minus p. This is the polynomial satisfied over Q. Accepted? Now, you can understand one more thing, that you can have a chain of fields. Each one is extending further like this. Q subset of Q of root 2 subset of Q of root 2 root 3 subset of, and so on. And I will say that this chain will never end. You cannot get a stoppage for this chain. They go on to continue. Even though if you take any different prime number, the different prime number will not belong to any one of the previous sets. It is an infinite chain. Since the prime numbers are infinite, so this is an infinite chain. So this is an algebraic extension having infinite number of elements. Therefore, every algebraic extension need not be finite. Clear? You take a note of that for an example. Now, I want to give some standard definitions for you, which will be interesting to you. So we have discussed about algebraically closed fields, normal extensions, splitting fields, etc., etc. Now we have one more thing, we call it as separable extensions. So compared to separable extensions, we are not having any problems under UPSC. However, I will give the idea so that if you have interest to study the results based on separable extensions, you can follow on your own. So some of the definitions are: a field is called prime if it has no proper subfield. If it has no proper subfield. Right? And you have one more definition, that what is meant by a perfect field. So a field is called perfect if each of its algebraic extensions are separable extensions. So what is meant by a separable extension? First of all, it must be algebraic extension. Second, each element is separable. You take a note of these results. So if you want some examples, every finite field is perfect. A field of characteristic 0 is perfect. And we will get a question that what is meant by separable element. So separable is nothing but if you take an algebraic element, that element satisfies a polynomial which has simple roots. It will not possess multiple roots. That kind of polynomial, we call it as a separable polynomial, right? I will give simple example that you take x square minus 2. This is the product of linear factors for this polynomial. So here root 2 is one root, minus root 2 is another root. Accepted? And root 2 is algebraic for this polynomial because root 2 is satisfying this polynomial. Now see, if you consider all the roots of this polynomial, all are simple roots, no root is repeated, all are distinct. Accepted? So root 2 is an element satisfying a polynomial which contains simple roots only. This element is algebraic as well as separable. This polynomial we call it as separable polynomial. So if the polynomial possesses multiple roots, let me say if you take a polynomial x minus 2 whole square. So what are the roots of this polynomial? 2 and again 2. So the roots are repeated. So if you take such kind of situation, we don't call it as separable. Okay? Clear to you? And there is one more definition, simple extension. So what is meant by simple extension? If you consider an extension E for F, this extension should be of the form f of alpha. In other words, this extension is generated by one element over f. This we call it as simple extension. So if you take a small example, if you take q and q of root 2, so q of root 2 is simple extension of q. It is having one element extra. Okay? And the result is finite extension of a finite field is always simple. Finite extension of a finite field is always simple. That was the result. So there are so many results based on separable extensions as well as prime fields and perfect fields, which we don't want to discuss now, because we cannot give guarantee that even though if you have the sessions on them, whether a question will be posed on them or not, we don't have the guarantee. So at this part, I want to conclude the discussion based on finite fields as well as extensions. The main constraints with regard to exam point of view are how to calculate normal extension, how to calculate splitting field, how to calculate the degree as well as dimension. Whenever extension is given, how to calculate the basis for it, and some standard results. These are enough with regard to exam point of view. Okay, rest of the things I leave them for you for your interest. So while following any standard textbook, you can solve any result on your own. If you have any result, if you have any doubt, you give a postage in Telegram. I will solve it for you and I will clarify your doubts. So for exam point of view, this thing is suffice for you, right? Because if we discuss a lot more, we will get an aversion over abstract algebra. What it is this thing? Up to groups and rings, it is okay. While going with fields, we have a lot of confusion. So if anybody is interested over this abstract algebra context, so there is a book having 2 volumes, Applications of Abstract Algebra. Maybe it is published by Oxford Press. So if you are interested, after the completion of your preparation, you randomly go through it. So there you can understand what is the real life importance of abstract algebra and how problems get solved by using abstract algebra context. And the very use is abstract algebra is mainly concerned with the polynomials. So whenever you get a application of polynomial in physics as well as chemistry and allied fields, there you can implement the context of abstract algebra. right? Now, I want to give the definitions as well as statements of silo theorems in group theory. So please understand, in the worst case, we can say that the proofs of the theorems will be asked. But in general, always they will ask questions based on silo theorems. So this is the last chapter with regard to abstract algebra. So in tomorrow's session, I will take problems based on silo theorems around 1 hour or 1.5 hours based on your interest. So in today's session, I want to give the statements as well as definitions involving silo theorems. Okay? You please take a note of them. So just give me a moment. I think everyone will know that a group means a set having a binary operation on it satisfying 4 properties: closure, associative, identity, inverse. So if you take a group G, we call this group as P group, where P is a prime number. Then if each and every element in the group has order P power R. So if you say this is G, every element in this set, if you calculate its order, it is P power R. Let me say I have taken P is equal to 3. A group G is called 3 group. If you take any element in it, it has order 3 power something, 3 power 0, 3 power 1, 3 power 2, 3 cube, like that. So you can understand one thing, that the order of the element divides order of the group. So since each element is having order P power something, the group itself is having order P power n. Because each element is having order P power R, therefore the group itself possesses order P power something. Okay? Right. Now, the first silo theorem states that whenever you take a prime number P and M is a positive integer with the property that P power M divides order of the group, then we can find a subgroup H of G such that order of H is equal to P power M. Right? Again, you take a understanding of the result. I have taken a group G. P is a prime number, M is a positive integer. If you say that P power M divides order of G, then you can find a subgroup for the group. The subgroup order is P power M. So for a simple understanding, let me say order of G is equal to 4. You take the prime number P is equal to 2. If you fix M is equal to 1, you say that P power M divides order of G. Agree? Yes or no? So we can say that for this subgroup, for this group, you can find a subgroup having two elements because p power m is nothing but 2 here. There is one more result based on the same thing, that if p power m divides order of g and p power m plus 1 does not divide order of g, you can have a subgroup. That is also true. So if p power m divides group order, p power m plus 1 does not divide group order, so the subgroup is having order p power m and it is a p subgroup. We call this subgroup as silo p subgroup. That means each and every element in the subgroup is having order p power something. So try to understand the values slowly. Clear? Try to understand them. So there are two more statements I want to give. The second silo theorem states that you consider any two silo p subgroups. Say this is a group G. I have taken two subgroups for it. These are silo p subgroups. Since silo has second condition is compulsory, means some authors stated that silo first theorem is p power m divides order of g implies you can find a subgroup having order p power m. Some authors defined that p power m divides order of g and p power m plus 1 does not divide order of g, then you will get a silo subgroup. Both are correct. Different textbooks have given differently, right? The subgroup, we are calling it as silo p subgroup. The prime number what you have taken, mentioning that prime number, we are calling it as silo p subgroup. Since silo has invented this technique and this formulation, we are calling with that name silo. So if 5 is the prime number satisfying that condition, we say that the subgroup is silo 5 subgroup. That's it. Okay. Right. Now, if you take a group G, you have two silo p subgroups, then the relation between them is they are conjugate. So what is meant by conjugate? Let me say this is one subgroup P, this is another subgroup Q. Then it is possible for us to write that P into G is equal to G into Q for some element G belongs to G. Or you can write Px is equal to XQ for some X belongs to G. In other words, you can write it as capital P is equal to XQ X inverse. They are conjugate. Okay. Any two silo P subgroups are conjugate. So what is meant by conjugate? This type of situation is possible. Are you clear? The third theorem states that if you are calculating the silo P subgroups, how many such subgroups will exist? How many such subgroups will exist? So, the number of subgroups, if you calculate, the number will be of the form 1 plus Kp. The number will be of the form 1 plus Kp, where 1 plus Kp divides the group order, and K is nothing but a non-negative integer. So K takes the values 0, 1, 2, 3, so on. K will not take negative values. That's it. So if you want to say, I have taken a group G, I know its order. If you want to know how many P subgroups you will get for the group, then the number satisfies this condition, 1 plus Kp, and this will divide the group order. These are nothing but 3 Silo theorem statements. Based on this, we will solve certain problems in the next session. The advantage of the Silo theorems is, if I mention that this is a group having this much number of elements, then immediately on observing the number pattern using Silo theorems, we can say that whether the group is abelian or not, simple or not, how many subgroups will exist. If I know order of an element, how many subgroups you can calculate having that element inside, how many cyclic groups you can find, all these things will be calculated if you have good knowledge over the Silo theorems. Whether the subgroup is a normal subgroup or not, whether the group itself is cyclic or not, all these things we can say by simply observing the number. Okay? That is the best part of Silo theorems. So at this point, I want to conclude our today's discussion. So we will meet tomorrow with problems based on the theorems.